Hello. Ojas, if you could confirm, am I audible or not? Ojas, are you there? Okay, I haven't received any response from you. So I hope my uh, microphone is working fine. So we shall wait another 5 minutes. We shall see if somebody joins other than you. And after that, we shall start today's session. Thank you. Okay, so I believe we can start with today's session. And I hope I am audible. And if I am not, you may inform me about that. Right. So, uh, my name is Aditya Sharma, and I am a research scholar at present uh, here in IIT Guwahati in the Department of Mechanical Engineering of our college. And I am pursuing my PhD degree under Professor Niranjan Sahu only. So this is Advanced Thermodynamics and Combustion course being conducted by IIT Guwahati only under this NPTEL program. Right. So the instructor of this course is Professor Niranjan Sahu, and I am the teaching assistant of this NPTEL course. Right? And I'll be taking the live tutorial sessions for this particular course, right? For this semester. Right? So this is our first tutorial session. Like this tutorial session, we will have in total 13 tutorial sessions, out of which 12 tutorial sessions will be based on the contents of different weeks that are the content of different weeks that is there in this course, right? So for each week there is one live tutorial session. So in this way, 12 live tutorial sessions, and at the end of these live tutorial sessions, we will have one extra tutorial session, or say course concluding session. So in that session, we will conclude briefly the whole course. Right? The whole contents of this course we shall conclude in that particular session. So that will be at the last of this course. Right? So the theme of this week was review of basic thermodynamics, right? And this live tutorial session will be of 2 hours. Every Sunday from 3 to 5, we will have these live tutorial sessions. And in case in some on some Sunday, if there is some change in the timing, or for that matter, if there is change in the day of the tutorial, that shall be communicated through the emails only. Like you are receiving these uh, for this, you have received the notification. Likewise, the notification shall be delivered. Right?
Uh, yes, sir. Karthik this side. Good
Yes.
evening.
Yeah. Good evening.
I just want to know one thing, sir. During the course of the time, will you be also dealing with any software type where we will be doing some combustion analysis and all?
No, 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 no. So because in this the structure of this course, we don't have anything like this where we have hands-on practice on some software. So
Okay,
that we won't be doing, because the uh, whole content of the this course has been already decided. So in that there is no such thing. So we won't
okay.
be doing that. Yes.
And what about the chemistry of combustion, sir? Say, for example, for petrol, diesel, and for the other fuels, we'll be dealing with that also, or it won't be direct?
Yeah, at the end of this course, there are a few uh, lectures, right? For this particular course only. So there we have something related to chemistry of combustion. So in
Okay.
those weeks we will be seeing all that.
Okay. Then okay. Okay. Okay.
Okay. So I have been conducting such I have conducted such live tutorial sessions in the previous semester. So those sessions were for fundamentals of compressible flow, right? So there, what we did, the structure of the whole tutorial session is like this. So we do it this way. First of all, briefly, I'll discuss the topics that have been covered in this particular week, right? And after that, we move on to the conceptual questions. So these will be multiple choice type of questions, right? Or true or false types of questions. Uh, After that, what we do is we take some numerical questions based on your assignment only, so that you are able to solve your assignments and you don't feel much problem in that, right? And at the end, then we conclude the session with all this. So three things are there. One is topics, briefly we'll discuss, then some conceptual questions we'll discuss, and after that we will have few numerical questions, right? So the basic idea of the tutorial session is that though we will be handling some uh, questions related to this week, but then we should be able to revise the week's content with this particular session, right? By means of questions only. So this is the whole idea of this tutorial session from my side, right? All right. Okay. So in this week we had three lectures, right? So first lecture, basically the main topic in that lecture was, so in this week basically we discussed the laws of thermodynamics, right? The crux of all these three lectures is that we discussed the uh, laws of thermodynamics in these three lectures. So in lecture one, we discussed our zeroth law, right? And in lecture two, we discussed first law of thermodynamics, and in lecture three, we discussed the second law of thermodynamics. So this uh, particular week is the basic review of thermodynamics, right? All right. So the first topic in lecture one was macroscopic and microscopic approach. So when we are trying to study some system, so what approaches we take into consideration? This all has been discussed in this topic. So for our thermodynamic analysis purpose, basically we use the macroscopic approach, right, as has been discussed in the lectures. So, and then for the microscopic approach, we deal with the kinetic theory of gases. So all that comes in the microscopic approach, right? And this has also to do with the scales we are dealing with, right? So microscopic approaches for the molecular level. So this all has been discussed in the lectures very well. Then we saw some terminologies related to study of uh, this heat, right? So in thermodynamics, like these are very basic terminologies, like what is an open system, and for that matter, what is a system, and what is a surrounding, and what is a closed system. So all these terminologies have been discussed in this particular topic, right? After that, we moved on to thermodynamic equilibrium and zeroth law. So here we brought the concept of equilibrium. So what is an equilibrium, and when do we say that a system is in equilibrium, right? And in relation to that, zeroth law was introduced, right? So we have the statement of zeroth law, right? Like if we have two systems with an adiabatic wall separating that, right? And if we bring another system, right, and this third system is connected to these two systems earlier mentioned, but by means of dithermic wall, in that case, they will be in mutual equilibrium, right? Thermal equilibrium. So also I should mention here that uh, I use the term dithermic. So dithermic basically means a wall across which heat can be transferred. Right? And adiabatic we have in our basic classes also studied that adiabatic is where there is no transfer of heat. So this is the zeroth law and thermodynamic equilibrium. And then by uh, means of this thermodynamic equilibrium, the concept of thermodynamic equilibrium and zeroth law, we bring into picture the concept of temperature. So when we say two systems are in thermodynamic equilibrium, how do we say they are in equilibrium? So then the concept of temperature comes into picture, right? Which tells that whether two systems are or two or more systems are in thermodynamic equilibrium. Then to quantify the temperature, temperature scales were introduced, but uh, the quantitative part of temperature we have studied in this week only, that it is the second law of thermodynamics through which we come into we bring into our discussion the quantitative part of temperature, right? Carnot cycle and all, right? But here also it has been mentioned the temperature scale and the measurement of temperature, like how do we measure temperature and what different scales are there to measure. Right? Okay. So after that, we have discussed a simple thermodynamic system, right? So this is there's nothing much in it. Simple. How a simple thermodynamic system is like, and what are the different elements of it. All this has been discussed in this particular topic, right? And then there is one subtopic to it, that is equation of state, where we saw the equation of states of ideal gas, right? So we saw two equations. So one was ideal gas equation, and then other was van der Waal this van der Waal equation, right? So basically, van der Waal equation is for real gases. So all this we will cover later uh, in the upcoming weeks of this course, right? But it has been mentioned in this particular topic directly, right? Okay. So this was equation of state. Then after that, we came to hydrostatic system, right? So what is a hydrostatic system and how it exerts pressure in all directions, right? It has to be isochoric, right? In all the directions, properties have to be same, right? That is yes, choric. Yes. No, yes. Wait, but that term I believe isochoric because is constant volume, but then there's some term maybe Uh, I'm not able to recall it correctly. So there is some term, so that has to be there for a system to be hydrostatic, right? Okay. Then along with the hydrostatic system, we uh, discussed few other topics like what is volume expansivity, right? For it, the numerically the formula for volume expansivity is this, right? At constant pressure, if there is a change in volume with the change in temperature, right? Right. So this is the uh, formula for volume expansivity, right? Then there is isothermal bulk modulus and isothermal compressibility. So all this has been discussed, but then I'll just write down the formula for isothermal bulk modulus, right? Right. And then inverse of this is isothermal compressibility, right? So conceptually, it has been well discussed in the lecture, so I won't take time on that. But so that we have some context of all these topics, I'm just briefly discussing all this, right? Right. And then some relation between volume expansivity and isothermal compressibility. This has been discussed in this particular topic, right? Volume expansivity and isothermal compressibility. So this was about lecture 1, and then in lecture 2, we introduced work and heat transfer. So what is work and what is heat? This has been discussed. This has been introduced in this lecture. And in the previous lecture, we discussed what is an hydrostatic system, and here we introduced one more term, that is quasi-static, right? So what is a quasi-static process, and along with that, how we consider work transfer with quasi-static processes. This has been discussed in this topic. So for a process to be quasi-static, the lectures say that the system has to be in thermal equilibrium. And for thermal equilibrium, it has to be in mechanical equilibrium and chemical equilibrium also, right? The content of lecture says this. Right. Then we saw a pressure volume diagram, right? So as far as the thermodynamics is concerned, PV diagrams are yes. So as far as the thermodynamics is concerned, this is, I was saying, PV diagrams are very important, right? So through PV diagrams, we can discuss the work indulged in particular process, right? Because the area of PV diagrams give us work, right? And then after that, adiabatic work has been discussed. So if we have a system where there is the walls, let's say, are adiabatic and there is no exchange of heat, in that case, if the work is either done on the system or work done by the system, in that case, what's the scenario, right? So this has been discussed. So for example, if an adiabatic uh, adiabatic work is done on an system, its internal energy increases, right? So, and then later internal energy function also has been introduced through the discussion of adiabatic work only. The concept of internal energy has been introduced, right? So this was about adiabatic work and internal energy, right? And then after that, there is a topic on generalized work and composite systems, right? So in composite systems, there are more than one system, right? More than one hydrostatic systems, and somehow we club these two systems, maybe by a diathermic wall, and then the system eventually we get is a composite system, right? And then generalized work has been discussed by means of generalized force and generalized displacement. And in our discussion, as far as our discussions are concerned, so generalized force is the pressure, and the generalized displacement is volume. Right? Then first law of thermodynamics was introduced, right? Which also is the law of conservation of energy, right? Which says that heat mathematically heat is equals to change in heat is equals to change in internal energy plus change in work, right? So this is our first law of thermodynamics, right? After discussions on first law of thermodynamics, heat capacity and its measurement has been discussed. So heat capacity basically, as the name suggests, so we have come across heat capacity a number of times in our previous studies. Uh, but here also we shall discuss this. So as the name suggests, it's the capacity of heat, right? So if a system is receiving some heat, then what is the capacity of that system to gain heat, right? And that we define using different heat capacities, right? Or should I say two terms, right? That is specific heat at constant pressure and specific heat at constant volume, right? So these heat capacities have been discussed, right? And then at the end of this lecture, modes of heat transfer have been discussed, right? So, sorry, three modes of heat transfer. One is conduction, then there is convection. After that, there is radiation. Right? So these three modes of heat transfer have been discussed. Heat conduction governed by Fourier law, right? And then we have heat convection, right? And then at the end we have radiation, right? In which the Kirchhoff's law, right, and Stephen Boltzmann law, these two laws have been discussed, introduced, right? So this is about the lecture two, right? All right. Then we have the last lecture, right, of this particular week. So here we started with the conversion of heat and work. Okay. So how heat can be converted into work and work can be converted into heat is the whole theme of this particular lecture. but in the starting slides, we saw that how work can be purely converted into heat, but then vice versa is not possible. And then for that particular thing, we introduced the second law of thermodynamics, right? So the statements of second law of thermodynamics state all that if we want to get work out of heat, then it is not possible to uh, convert 100% of heat into work, right? So for heat engines, there is a Calvin Klein statement, right? And then for refrigerators, there is a Clausius statement. All these statements we have studied in are these plus one and plus two standard also, right? And then after these statements, there are inferences out of these statements that have been discussed uh, in this particular lecture. Sorry. And then after that, there is concept of reversibility and irreversibility has been discussed. So, what is an reversible system, right? So, if you can bring some system to its initial state, right? And then there are a few conditions attached to it. So, this way we define what is reversibility, right? And then opposite to that is irreversibility, right? After that, we discussed Carnot cycle and your assignment, right? Your assignment for week one is based on this Carnot engine only, right? Yes, few questions are. One question is on, I believe, Carnot engine. One is on heat pump, and then is on the refrigerator. One is on the refrigerator. Okay. So then we discussed our Carnot cycle, right? Yes. So, what is the peculiarity of Carnot cycle, and why do we discuss Carnot cycle a lot? Right. So, the main thing about Carnot cycle is that the efficiency of this particular cycle is maximum in any case, right? Out of all the heat engines, right? This is the particular cycle in which we will have the maximum efficiency, right? So its PV diagram is like this. Right? For our future reference, I'm drawing this, right? Something like this.
Hello.
Yes, yes,
Yes, can
yes,
I ask some query?
yes, please.
Yes, actually, in this topic of reversible and irreversible process,
Yes,
okay, can you please throw some light on internal, internally reversible and externally reversible?
okay.
And any like see Carnot is internally and externally like we can have that it is a complete reversible process. But when we talk about different processes,
Yes,
so which are the processes where this externally irreversible and particularly internally irreversible or reversible?
yes.
How,
So,
with respect to practical examples, can we have any illustrations?
what the thing is, sir, that as far as this these tutorial sessions are concerned, so
Hmm.
we do our preparation basically focusing on questions only, right? So I go through the lecture slides, right?
Okay.
and then I prepare some questions based on that.
Okay.
The question you are asking is conceptual question. These are good questions, but then for that I'll have to refer to the book because I have taken this course also. So I
Okay.
can recall that in Shapiro book, right? These topics have been discussed very well in detail. But at
Okay.
this point of time, I haven't prepared this session in that manner, and
Okay.
also I haven't revised all those
Okay. No
details.
problem.
Yeah, yeah.
Fair enough. I appreciate because these are very profound questions, and
Yes, yes,
it needs some amount of perspective building before you deliver.
yes,
So maybe whenever in next session when we meet, or
yes.
if you have any such material, you can post it on the group.
Sure, sure. You just, I'll just jot down whatever you have, topics you have said. You can
Okay.
just, once again, you can,
Internally and externally, irreversibilities are again classified into processes. Processes can be classified further into internally reversible or externally irreversible.
yes,
So,
yes.
like this, there are some theoretical treatments in different books,
Okay.
but
You want some
practically,
practical
yes, yes.
examples you want, sir?
Yes, yes,
Yes.
because this is
Okay.
an advanced thing. So,
Yes,
for advanced learners, maybe
yes,
especially
yes,
for faculties, this will be your domain expertise, you or maybe also our formal course instructor. They can
yes,
give some good perspective
yes,
on
sure,
this.
sure, sure.
Yeah, yeah.
Okay. Okay. Thank you. So maybe in the next tutorial session, I'll just briefly discuss a few practical examples on the topic you
Thank
have
you.
just mentioned.
Yes,
Yes, correct.
thank you.
Okay, all right. So this is our Carnot cycle, right? Okay. So in this 1 to 2 is adiabatic, right? Compression. Then this is isothermal heat addition, right? Then this is also adiabatic expansion, and here is isothermal heat rejection, right? 4 to 1. So this is our uh, basic Carnot cycle. So we have discussed this in this particular topic of Carnot cycle, right? After that, we move on to the next topic, that is thermodynamic temperature scale. So here, what we see is that in the zeroth law of thermodynamics, we introduce the concept of temperature. Right? But there we were not quantifying the temperature, though we discussed how the temperature is measured. We introduced that and the different scales. But then, if as far as the theories concept of is concerned, so the quantitative element of the temperature, right? This comes from the second law of thermodynamics, as the content of your lecture 3 also says. So here, when we discuss Carnot efficiency, right? There we see that the Carnot efficiency essentially depends on temperature only, right? And from that thing, we come into this quantitative part of temperature, and this way we define thermodynamic temperature scale, right? And then there are different temperature scales, as we all know, some very basic and common, like Celsius, Fahrenheit, right, Rankine, and then one more is there, Kelvin, right? So all this has been discussed in this particular week, right? So Now we shall move on to the conceptual questions. Right? So I have what I do is that with along with the question, I also mention the topic from where this particular question comes, and then uh, we discuss on particular question as far as possible, right? And this way we discuss our question, right? So first question is on macroscopic and microscopic approach, right? And this question says that, so these are some questions will be very straightforward and basic, but then the idea is also to revise the content that has been covered in the lectures, right? Along with that, you might also find some questions that you feel that are good questions, okay? And then at the end, there are numerical questions that on the same line as have been given in your assignments. So that will prove to be handy to solve your assignments, right? So I have a couple of questions, conceptual questions, but then if the time doesn't allow, so we will skip some conceptual questions, and we will at the end, in the last few minutes, we will do our numerical question. Okay? In maybe last 20 minutes, we will do our numerical question. We have three numerical questions we have, but then conceptual questions are a lot. So we will see how it goes. Right? So the first question says that the study of thermodynamics mainly involves the understanding of dash temperature dependent phenomena. So uh, these are the four options. So maybe someone can answer.
Yes, I think so. Option C, both microscopic and macroscopic.
Anyone else?
So I also suggest that the question, if it is specifically saying suggesting study of classical thermodynamics, then it
Yes.
should be macroscopic. And if it is statistical thermodynamics as a whole, thermodynamics will have statistical thermodynamics. Then it will
Yes.
have microscopic perspective also.
Yes. So, because in this particular course, we basically are dealing with, though I should have specified, but then we are in this course, we will be, I believe, discussing classical thermodynamics only. So that question was from that perspective only. So I have given the answer from that perspective. So yes, the answer to this question, like if sir was saying, if it has to be statistical thermodynamics, if has to be considered, in that case, yes, C is there. But then because in this particular course, we are dealing with classical thermodynamics only. So this question I had made from that perspective only. So I have kept it question, the answer to this question as microscopic. So this is from lecture one. So first, this is the first topic of macroscopic and microscopic approaches that are considered in our thermodynamic studies. Okay. Then next question. So this question is from the terminologies related to thermodynamics, thermodynamic studies, right? So the question here is: the boundary that separates a system from its surrounding has a finite thickness. So when we talk about a system and about its surrounding, and the boundary separates a system and its surrounding, in that case the boundary we are discussing whether it has some finite thickness or not. This the question asks, and it's a true and false type of question. Yes, any answer, please? Otherwise, I'll discuss this question. Okay, Sanvi says false. So, yes. So this boundary concept basically is it's not uh, as if this is some boundary that has some thickness or it's some physical boundary. So it's a concept. This boundary that separates a system from its surrounding, right? It's a hypothetical concept, right? So there is nothing like a physical boundary as such which has a finite thickness when we talk about boundary in this perspective, in this context. So this boundary doesn't have basically anything. So if the question says that if it has some finite thickness, in that case, the statement is false. Okay. Then moving on to next question.
Aditya ji,
Yes, sir.
so sorry to interrupt and
Yes.
also to bother, but just I have a small observation or a suggestion.
Yes.
Uh, so it will be very nice. Like I am seeing, you have quite in detail chosen the questions,
Yes.
but at least for this MCQ type of questions, if we float a Teams form here for so we can give the answers quickly, and then it will be more interactive. If we are getting wrong or correct, we can get some uh, at on the if everybody is getting that correct, then we can move ahead to the whatever you were saying at the end. Maybe that time will be for numericals. uh, so if that is
Yes.
possible from maybe next classes, it will be really nice. Uh, I'm being a teacher, maybe I should not. Here I'm a student, but like this, sometimes I found out in my class, like this kind of practices, this keep students very much curious if they are getting wrong, and then they will wait for your explanations and like this.
Yes. So your like I uh, admire your suggestion, right? And I also respect your suggestion. Also, you have told that you are a teacher, and I keep very high regard for you, sir. But the actually the scheme under which I am conducting these tutorials. So also I have to record these sessions. So uh, whether like logistics, I believe maybe that will be too much for me. Like if I float some
Okay. Okay,
form.
Aditya, it's fine, perfectly fine. You can carry on.
Yes.
It is just like a
No, no,
suggestion.
yes, session. I yes, no,
And if, even if it is discussed, then that is completely fine due to the logistics issues and your
yes,
our requirements. It
yes,
will this MS, because it was in MS platform. Like then
yes,
there are these forms are available, and
yes.
but it is fine. You don't have to any explanation. That is fine. It is just a suggestion. Just
No,
fine.
yes. But
I
if
don't
it
intend to. I don't intend to criticize or
no, no, no.
say something.
I take
Yes,
it very positively. I take it
yes.
very positively. But this session is also new for me, so that's why, for the safer side, I'm saying that logistically whether it will be feasible or
It is
not, because
quite very straightforward. Like with this MS forms in the same meme, like Teams meeting, like that
yes,
forms are like freely available. Like
yes,
so, it should not be big thing. Like just like right now, I'm feeling that these are because the course suggests that it is advanced thermodynamics. So many of
yes.
the maybe participants are expecting some advanced
Uh,
treatment.
yes, actually, this because this is the first course
Yes,
and
yes.
first week of this, so that's
Okay.
why
Okay.
all these questions.
Sure, sure, sure.
Yes,
Okay.
yes. Because
Please
in the
carry on. Thank you.
yes, 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 in the coming weeks, the topics on combustion and then this exergy, all this will be covered. But I do take your suggestions very positively. But then, if I'm able to do that, I'll surely do that. But in case I'm not able to, like,
It's perfectly fine,
yes, yeah,
Aditya.
please
No
don't
problem.
mind.
No problem.
Please
No
don't mind.
problem. No problem at all.
Yes, thank you. Okay, so moving on to our next question. So this question is on thermal equilibrium and the zeroth law. Right? So the question is in fill in the blanks type of format, and the question says the scientific understanding of temperature is built through dash equilibrium established through dash law of thermodynamics. Yes. So this is pretty straightforward. That is too straightforward because I have already given the topic also, right? So I have discussed this earlier also. So zeroth law, when we discuss, we introduce the concept of temperature through zeroth law of thermodynamics only, right? And in that in this law we discuss the equilibrium in terms of uh, thermal, right? We discussed the thermal equilibrium by means of zeroth law, and the question is pretty straightforward. So the first blank will be thermal, and then the second will be zero of thermodynamics. So Sanvi has already answered this question. Right? So B is the correct option to this question, right? So moving on to next question. So this question is on temperature scale. So there are two absolute temperature scales, right? Out of the options given. So which are those two absolute scales you have to mention? So there are two temperature scales that are absolute in nature. So by absolute, what we mean is that if in that scale we have a numerical value 0, in that case there is no temperature possible in this universe that can go below that particular mark, right? So that is the meaning of what an absolute temperature scale is. So in that case there are two temperature scales, right? So one is Kelvin and the other one is Rankine, right? So these are two scales for which if there is some numerical value 0 in this scale, so in that case there is no temperature possible below that mark, right? So that is uh, the absolute temperature scales. Right? So yes, the answer to this question is C. Right? So we will take one more question. After that, we will have a 5 minutes break, and then after that, we will again start the session. Right. So just we will take one more question. So this question is on temperature scale, and the question says that the absolute temperature scales solely depend on triple point temperature of water. Whether this is true or false. So if we have to define some absolute temperature scale, in that case, we can do that by using triple point temperature of water. So whether this statement is true or false. So if we have to define some absolute scale for temperature, right? like Kelvin scale is there and Rankine scale is there. In that case, we can do that just through the triple point temperature of water. Through this particular temperature point, right, we can define our absolute uh, temperature scale. So in case of Kelvin scale, if you see, triple point is at 273.16 Kelvin, right? That is that is 0 degrees Celsius, right? Also, and then in case of Rankine, that is 459.67 degree R. Yes, so answer to this question is yes, true. All right. Okay, so it's 4 p.m. at present, right? 1 hour has passed since the start of the session, so we will just take a quick 5 minutes break and then we shall start. We will continue with the session, remaining 1 hour. Okay, thank you. Okay, so let's continue with the session. So Karthik says, hi, please do say for the analysis of advanced combustion in relation to IC engines, are there any online free software available? First is this question, and then secondly, he says, and have you done any MATLAB related solutions which you would have done considering advanced thermodynamics? Okay, so Karthik, the thing is, my specialization is fluid dynamics. Okay, so currently I work on fluid dynamics related problems. Right? Yes. So
Yeah.
Karthik, I was telling you that uh, you have said that can I suggest some software, right? So I'll tell you that my research here is basically on fluid dynamics, right? I work here in gas dynamics lab, and in the gas dynamics lab we have shock tubes. So I am currently working on some setup related to shock tubes, right? As far as this particular course is concerned, so I have taken this course as a coursework here in IIT Guwahati only, right, in my first semester. So for this question, so I won't be able to suggest some software for, I believe, simulating combustion related some problem, right? This is what you're saying. And then same is related to you're saying using MATLAB if I have done some solution related to that. So that too also because the course didn't uh, uh, include anything like that, so I haven't done that, right? But then if there is some guy of this specialization and he is using something like this in his research, so definitely I can ask that person and then he can suggest that, right? So in that manner, maybe I can help you in that way, but then directly it won't be possible for me. Right? I hope I have answered your question, Karthik.
Actually, what Ojas was saying, the same expectation I have also come from. Because I'm basically
Okay,
working in an industry, in OEM industry, that is related to engines.
okay,
So now the trend is towards hydrogen and all. So I felt that we'll be getting some practical solutions on applications of the thermodynamics in a real-time condition. That is, for me, it is IC engines.
okay, okay.
So so that's the
So
reason. Because yeah, because uh, the basics.
yes,
If I have joined, I would have said that okay, I've joined the basics, and I need to cope up with the content of work which is being presented now. But
yes,
since I have joined with the advanced thermodynamics, I felt that such kind of real-time
yes,
applications will be more
yes.
considered in this
Right,
curriculum.
right, okay. Okay, so basically the thing is that the course, I do not design this course actually. So the courses are designed by professors only, right? And then
Mhm.
whatever the professor communicates to me the content, using that content only I prepare my tutorials, right? And in this course also in the later weeks you will also see that uh, there are not such things like some hands-on experience on some software or
Mhm.
something related to simulation based on combustion is
Mhm.
there. So Even I don't know if whether it is, I don't think also explicitly it has been mentioned in the information related to this particular course. So in that case, from my part, sorry, I won't be able to help in that context.
Okay, but at least we expect that the mentor should be well thorough with the advanced thermodynamics. Even though if it is not in the course, we expect that the
Yes,
mentor should have an in-depth knowledge and at least the guidelines, or he should be able to guide us the types of books or the things which
yes.
are available
See, see,
in the yeah,
see.
yeah.
What I'm saying is, whatever has been covered in the course, I can deal with that, right? In whatever way the course has gone through in our college, right? So in that manner, in that direction, I can help in whatever way I can uh, help you, right? But beyond
Okay.
that, because also it's not my research area, right? So I do my research, and then this is my teaching assistantship. So I cannot uh, indulge too much into this topic in terms of research. Right? This is my point. And if you're saying that you have some queries, so I can consult somebody
Mm.
if there is some person who is of this research, so that can be done. But beyond that, it won't be possible to do for me. I hope you understand.
Mm. Okay, sir. Sure, sure. Okay. Mm.
Okay, so the next question is based on hydrostatic system, right? So the question says that any system of constant mass and composition that exerts uniform hydrostatic pressure to the surroundings is referred to as a hydrostatic system. Right. So this is this, yes. So there is one particular term in this particular statement that is missing. So whether this statement is true or false. Please try to answer this question. So whether this statement is true or false. So basically, the whole statement is all correct, but then what kind of system has to be there for a system to be hydrostatic, right? So the system needs to be isotropic, right? In that case, only we can define whether a system is hydrostatic or not. So if that term is missing, so we cannot define a hydrostatic system, right? So in that case, this becomes a false statement. Okay, so moving on to next question. So next question is on volume expansivity. And the question says that average coefficient of volume expansion is defined as the ratio of change of dash per unit dash to the change in fill in the blank when the changes occur at constant fill in the blank. So there are four options. Please let me know what will be the answer to this question. Okay, so I have one answer, that is D. So this is basically the definition of average coefficient of volume expansion, right? That we have seen earlier also. So I have written it here, right? So this is it. So if we see this, there has to be constant pressure involved in it, right? And then there is change in volume, right? Per unit volume to that change in temperature, right? If you see this formula, this change in temperature, right? And so D option is correct, right? All right, so this was our seventh question. So moving on to next question. So this question was on volume expansivity. So the question says that the eighth question again is on volume expansivity, and the question says that the value of average coefficient of volume expansion is always positive. So whether this statement is correct or not. So this statement basically is false. Why so? Because it's not always the case that with an increase in temperature your volume will increase, right? So this has been given in the content of lecture 1 that there is one special case of water between 0 degrees Celsius to 4 degrees Celsius, right? In that case, if you increase the temperature, there is decrease in volume. So if the statement says that this average coefficient of volume expansion is always positive, in that case, it will be a false statement. Okay? So B option is correct. So moving on to next question. The question is on quasi-static process and work transfer topic. And this is question number 9, and it says that the ideal way of change of system is quasi-static, for which the system is infinitesimally near the state of thermodynamic equilibrium all the times. So whether this statement is correct or not. So if we know the definition of what a quasi-static process is, in that case, this statement should not be any problem. So this is basically the definition of quasi-static process only, right? So the ideal way of change of a system is quasi-static. So if a system has to change its state, right, from state 1 to state 2, so the ideal way is that it does it by means of a quasi-static process, right, which essentially has to be in thermodynamic equilibrium all the time, right? So this statement is true, right? So moving on to next question. So this is based on quasi-static process and work transfer. And the question says that it is not a must condition for a system in thermodynamic equilibrium to be in chemical equilibrium. Whether this statement is correct or False. Any answer? Okay. So Ojas sir says that this is a false statement. So this is a false statement because for a system to be in thermodynamic equilibrium, first it has to be in mechanical equilibrium, then it has to be in chemical equilibrium. Then only it qualifies for to be in thermal equilibrium, right? So this statement is a false statement. Right. Then the next question is on pressure volume diagram, question number 11. So it says that the hydrostatic work is independent of path. Whether this statement is correct or not. Okay. So I have one answer that is false. So if we talk about the hydrostatic work, so basically it is path dependent, right? So if even if we see our PV diagram, right, and through that if we try to try to find our work, right, so we'll have to integrate, and if we integrate this PdV, right, so in that case if you see see the P term, right, so it is path dependent. The way P behaves in PV diagram, that defines how the hydrostatic work would be, right? So if the statement says that the hydrostatic work is independent of path, in that case it will be a false statement, right? So this is a false statement. All right. So it's 450, 440, right? So in the last maybe 15 minutes, I'll take numericals. So I can again. So about this also I am saying that I know the definition of hydrostatic system, and from that context only the hydrostatic work I have put it here, and this you can find in the content of lecture 2 of this particular course, right? And because you have said you want some example on that, so I'll also look into that.
So, this hydrostatic work, is it same as flow work?
whether hydrostatic work is same as flow work. This is what you said.
Yes. Yes.
Sorry, I won't be able to answer that.
Okay. Okay.
But yeah, so but I'll go through the example of hydrostatic system and let you know. So there is another query you had on internally and externally reversibilities. From there also you want some example, right? So that I'll also look into that. Right? So moving on to next question. So next question is on adiabatic work. So there is R dash paths by which a system can change from an initial state to the final state by performance of adiabatic work only. So this question is about the paths that a particular process takes, right, to move from one particular state to some other state while remaining adiabatic. In that case, whether it can be done through some particular path only, or there is there are some other paths also through which this can be attained. So this is the question asks. So yes, what will be the answer to this question?
I can't answer this because diabetic work concept is not known to me actually. What is
Okay.
is it some different work, diabetic work?
So if we talk about adiabatic work, so it basically depends on the initial and final positions only, right? And it can take n number of paths. So the final work will remain same, right? Because there is no exchange of heat in that case. And when we were defining the internal energy, so uh, in that topic also we discussed that if there is adiabatic work that can be directly linked to the internal energy, right? So it depends on the initial and final states of the system. So any path it takes, the work depends on the initial and final state in case of an adiabatic work.
So, like, see, any form of work is a path function. So,
Uh,
it
uh,
any work. So, if
no,
it is a
not any work function is a path function. So if the work is adiabatic, in that case it won't be the same case.
can you elaborate? See, because mostly like forms of work, like one thing is, let us say, if there is a VDP kind of work and PDV kind of work.
Yes.
So flow, and then this flow work will also get accumulated in VDP. So
Yes.
this two works in general, any thermodynamic work if we define, but
Yes.
ultimately if we are able to raise the dead weight using pulley and rope arrangement, then we can categorize that kind as a work. So at
Yes.
that, I think so. If adiabatic work by that, the question is suggesting that the work which was calculated or demonstrated when the adiabatic process was enforced.
Yes. Yes. That is the point.
Yes. So, but in any process, like let it be adiabatic or isentropic, work will be path function. So, so, so I think so. It should be infinite paths.
Yes. 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 That is the answer. That is what.
But somehow what is happening is the diabetic is pulling a lot of attention, but
Okay.
conceptually I have not read about any diabetic, like philosophically, any like this
So
tag is bit misnomer, I suppose.
no. So this is covered in slide 12 of lecture 2.
Okay, okay,
So you can refer to the
I will again go through the lectures. Yes,
uh,
thank you.
page 12 of slide 12 of lecture 2.
Okay,
You can go
okay,
through
fine, fine, thank
that.
you.
Okay. Yes. So all right. So the answer to this question is D. Right. So I believe now we are left with maybe 12 minutes. So maybe one more question we can take after that. We will do numericals. Numericals. So the question is based on first law of thermodynamics. So it's on sign convention. So generally there remains a confusion on sign convention of heat and work when we are studying thermodynamics. So from that perspective, I have placed this question and the next question in this tutorial. Right? So so this question says that as a sign convention, heat is positive when it enters the system and negative when it leaves the system. Whether this statement is correct or not. So this is, so I'll answer this question as we are short of time. So this is a correct statement, right? And with this, I'll just go through the next question also because that is linked to the previous question only. So as a sign convention, the work done is negative when it leaves the system and is positive when it enters the system. So whether this sign convention has been correctly placed here. So this is not a correct statement. So when work is leaving the system, in that case it will be positive, and in case work is done on the system, then it will be negative, right? So this is the sign convention related to work and heat, right? So still we have some time, but then we will see the numerical question. There are three questions only, so it's not a big thing, but yes, let's see. Okay. Right. So now we are into our numerical questions. So there are three numerical questions that we'll be discussing from here onwards. Right? Just give me. Okay. So question is on conversion of heat and work. All right. So this is covered under conversion of heat and work topic in lecture 3. And the question says that what is the coefficient of performance of a refrigerator that operates with Carnot efficiency between temperatures of minus 10 degree Celsius and 40 degree Celsius? Yes. So, so we have two temperatures, right? One is minus 10 degrees Celsius and then one is 40 degrees Celsius. So to use these temperatures in our numerical, so first what we will do is we will convert it into Kelvin, right? So that will be 1073.16. That will become 263.16 Kelvin. And here it will become right. So now that we have these two temperatures, we will find COP, right? That is nothing but temperature low, temperature high minus temperature low, right? So temperature low here is 263.16 and temperature high to temperature low is 50, right? So this is our temperature low and this is our temperature high. Okay? And this comes out to be 5.26, right? So this is our COP. Right? So this was question number 26. So coefficient of performance of the refrigerator will be 5.26. So moving on to next question. Conversion of heat and work. So the question says that a heat pump uses 170 joule of work to remove 230 joule of heat from the lower temperature reservoir. Okay. So 230 joule of heat is to be rejected, and for to reject that amount of heat from the low temperature reservoir, a work of 170 joule is being done, right? So in that case, how much heat in joules would be delivered to the high temperature reservoir? So I'm using the nomenclature that is used in the lectures, right? So the heat that is to be rejected is 0, right? And for this work that is being done is 170 joules. In that case, the total heat that will go to the high temperature reservoir, right? That will be equal to QL plus W net, which is plus 170. Right? So 400 joules will be the answer to this question. Okay, so moving on to the next question. The next and last question for this tutorial session. So again, this question is on conversion of heat and work. So it's already 5 p.m. So we'll just quickly do this question and then we will conclude today's session. So the question says that a Carnot engine has an efficiency of 25% and its efficiency is to be increased by 35%. By what amount the temperature in Kelvin of the source is required to be increased in the sink if the sink is at 300 Kelvin. So the sink where the heat is being rejected is at 300 Kelvin, and then different efficiencies are given. So they ask for the increase in the temperature, right, at the source. If the efficiency is to be increased from 25% to 35%. So So efficiency, if we see, is 1 minus T low by T high. This is efficiency. So let's say for 0.25 efficiency, the temperature at source is TH1, right? And then T low is 300 Kelvin, we know. TH here we will write as TH1, right? Implies 300 by TH1 equals to 0.75. Implies TH1 equals to 300 by 0.75. That is equals to 400 Kelvin if you calculate. And then for the second case, when the efficiency is 0.35, in that case, we will write the temperature at source as TH2. So this will come out to be 461.53 Kelvin. So if we see the temperature has to be increased from 400 Kelvin to 461.53 Kelvin. In case the efficiency of this Carnot engine is to be increased from 0.25% to 0.35%. Okay. So this was it, right? Sorry. Right. So I'll conclude now this session. So in the starting, we discussed the three lectures, lecture 1, 2, and 3, and briefly we discussed the topics that have been discussed in this particular week, week 1. And after that, we moved on to conceptual questions, where we discussed a few questions from lecture 1 and lecture 2, and still there are some questions left in this tutorial that I had prepared. So what I'll do is, so I'll place this presentation in the Google Drive, and the link shall be shared with you by the NPTEL team. And along with that, because this session is being recorded, so what we do is we upload this session on YouTube, and the link of this session shall also be provided uh, by means of link in a Excel sheet. So from that, this session can again be watched. Right? So after conceptual questions, we did some numerical questions. So the numerical questions will prove to be useful in solving your questions that have been given in the assignments. Right? And in this way, we'll conclude the session, and we will meet again for the next session on next Sunday at the same timing, that is 3 to 5 p.m. Right? Till then, I'll just say thank you. Thank you for your time, and uh, happy learning. Right. Thank you.